Hey, I'm Noggs, and this is Noggs House. Today we're going to talk about stellar alchemy, the formation of stars. You've probably heard people say we are made of stardust, and it sounds really poetic and beautiful. But here's the cool thing. It's actually scientifically true. Almost every element in your body, the carbon in your muscles, the calcium in your bones, the iron in your blood, the oxygen you breathe, all of it was made inside stars billions of years ago. This isn't just a nice saying, it's real science. Today we're going to explore stellar alchemy. Alchemy is an old word that means transforming one element into another, like turning lead into gold. Stars are the universe's alchemists, and they're incredible at it. Through their life cycles, and especially when they die in massive explosions, stars create nearly every element that's important for life. We're going to trace this amazing journey from the simple elements made in the Big Bang all the way to complex elements scattered by dying stars, the cosmic ingredients that eventually became us. Let's start with what the universe had to work with right after the Big Bang. There was the Big Bang nucleosynthesis. It was the process that formed the lightest elements, specifically hydrogen, helium, and tiny traces of lithium. The early universe was about 75% hydrogen, the lightest element with just one proton, about 25% helium, which has 2 protons, and tiny amounts of lithium, which has 3 protons. That's basically it. All the other elements, carbon, nitrogen, oxygen, iron, gold, everything else didn't exist yet. The universe needed stars to make those. So these 3 simple elements, hydrogen, helium, and a bit of lithium, were the only raw materials available. Gravity pulled these primordial elements, primordial means from the very beginning, together into huge clouds of gas. When enough gas gathered together and got squeezed tight enough, the pressure and heat in the center became so intense that the first stars ignited. These primordial elements were the fuel that would power stellar alchemy for billions of years. So how does a star actually work? Stars form from nebulae. Those are giant clouds of gas and dust floating in space. When gravity pulls enough of this gas together into one spot, it gets squeezed tighter and tighter and the center gets hotter and hotter. Eventually the core gets so hot, about 10 million degrees, and so dense that something amazing happens. Nuclear fusion begins. Fusion means joining things together, and nuclear fusion means joining atomic nuclei, the centers of atoms, together. In the core of a star, hydrogen nuclei, which are just single protons, slam into each other so hard that they stick together. When 4 hydrogen nuclei fuse together, they make 1 helium nucleus. This process releases a tremendous amount of energy. That's what makes stars shine. This stage is called the main sequence, and it's the longest part of a star's life. Our sun has been doing this for about 4.6 billion years and will keep doing it for another 5 billion years. The energy from fusion pushes outward while gravity pulls inward, and these two forces balance each other. That's why stars are stable for so long. During this whole time, the star is basically a giant hydrogen to helium converter. Eventually, after millions or billions of years, a star runs out of hydrogen in its core. When that happens, there's no more fusion energy pushing outward, so gravity wins and the core contracts, squeezes inward. As it contracts, it gets even hotter, kind of like how a bike pump gets warm when you squeeze air. When the temperature reaches about 100 million degrees, something new can happen. Helium fusion begins. This is called helium burning, even though nothing is actually on fire. It's nuclear fusion, not chemical burning. 3 helium nuclei fuse together through something called the triple alpha process. It's called alpha because helium nuclei are sometimes called alpha particles. When 3 helium nuclei combine, they make 1 carbon-12 nucleus. Carbon is super important. It's one of the essential elements for organic chemistry, which means the chemistry of life. Without helium burning in stars, there would be no carbon, and without carbon, life as we know it couldn't exist. So every bit of carbon in your body, and you're about 18% carbon, came from helium burning in ancient stars. For really massive stars, ones that are at least 8 times heavier than our sun, the story doesn't end with carbon. These stellar giants keep going. Once the helium is used up, the core contracts again and gets even hotter. When it reaches about 600 million degrees, carbon fusion can happen. Carbon nuclei fuse to make neon and magnesium. Then when that's done, neon burning starts at about 1.2 billion degrees. After that comes oxygen burning at around 1.5 billion degrees, which creates silicon and sulfur. Finally, silicon burning happens at a scorching 2.7 billion degrees, creating iron and nickel. Here's what's really cool. These burning stages happen in layers like an onion. The star has different shells of fusion reactions happening at different depths. The outermost shell might still be burning hydrogen, while deeper shells are burning helium, carbon, oxygen, and silicon, all at the same time. But here's the thing. Each stage burns faster than the last. A star might spend billions of years burning hydrogen, thousands of years burning helium, but it burns silicon for only a few days. It's like the star is rushing toward its end. Silicon burning creates iron 56, and this is where things get really interesting and dramatic. Up until now, every fusion reaction has released energy. That energy is what keeps the star shining and holds it up against gravity's inward pull. But iron is special. Iron is the most stable nucleus in the universe. If you try to fuse iron into something heavier instead of releasing energy, it actually takes energy away. It's like iron is the bottom of an energy hill. You release energy rolling down to iron from lighter elements, but you have to put energy in to climb up from iron to heavier elements. So once a massive star has built up an iron core, and this iron core can be as massive as our entire sun, fusion just stops. Suddenly, there's no outward pressure from fusion to balance gravity's inward pull. The star has reached a dead end, and gravity is about to win in a spectacular way. The iron core can't generate any energy to support itself, and that leads to one of the most violent events in the universe. With no fusion energy to hold it up, the iron core collapses. And when I say collapse, I mean it falls inward incredibly fast. In less than a second, a core the size of Earth shrinks down to something about 20 kilometers across. This releases an absolutely enormous amount of energy. The collapse is so violent that it bounces back, sending a shockwave blasting outward through the star. This is a supernova explosion, one of the most powerful events in the universe. A single supernova can briefly outshine an entire galaxy of billions of stars. During this explosion, something crucial happens for element making, the rapid neutron capture process, or R process for short. Neutrons are particles in atomic nuclei that have no charge. In the extreme conditions of a supernova, there are so many free neutrons flying around that atomic nuclei can capture them rapidly, sometimes multiple neutrons in just seconds. When a nucleus captures neutrons, it becomes heavier and heavier, eventually becoming unstable and transforming through radioactive decay into heavier elements. This R process is responsible for creating about half of all elements heavier than iron, including precious metals like gold, platinum, and uranium. Every gold ring, every platinum metal, every bit of uranium on Earth was made in a supernova explosion. Supernovae aren't the only way to make heavy elements. There's also a slower, gentler process that happens in certain types of old stars called asymptotic giant branch stars. That's just a name for a late stage in a star's life when it's really puffed up and unstable. In these stars, the slow neutron capture process, or S process, takes place. Unlike the R process in supernova, where everything happens in seconds, the S process works over thousands of years. Nuclei capture one neutron at a time very slowly. After capturing a neutron, the nucleus might sit around for years before capturing another. Sometimes the nucleus undergoes beta decay. That's when a neutron inside the nucleus transforms into a proton, changing the element into a different one. Through this slow, patient process, the S process creates about half of the heavy elements in the universe, including elements like strontium, barium, and lead. So while supernovae are like explosive element factories, asymptotic giant branch stars are like slow-cooking element kitchens. When stars die, they don't just disappear, they give back to the universe. This is called cosmic recycling, and it's how the universe gets richer and richer in heavy elements over time. Low-mass stars like our sun will eventually become planetary nebula. Even though it has nothing to do with planets, it's just a name. These dying stars release elements like carbon, nitrogen, and oxygen that they made through fusion. Massive stars die much more violently in supernova explosions, blasting all their newly made elements into space at tremendous speeds. All this material, the star stuff, spreads out into the interstellar medium. That's the fancy name for the gas and dust between stars. This enriched material then becomes part of new nebula, new gas clouds that will eventually collapse to form new stars. But now these new stars form from gas that contains not just hydrogen and helium, but also carbon, oxygen, iron, and all those other elements made by previous generations of stars. This is how the universe gradually builds up its supply of heavy elements. Our sun is actually a third-generation star. It formed from gas that had already been through at least 2 cycles of star birth and death. That's why our solar system has rocky planets and life. Earlier stars made the elements we needed. So there you have it, the amazing story of stellar alchemy. Stars took the simple hydrogen and helium from the Big Bang and transformed them into all the diverse elements we see around us today. Through billions of years of fusion in stellar cores, through gentle release in planetary nebula, and through violent supernova explosions, stars have created the periodic table of elements. This process directly connects us to the cosmos in the most literal way possible. Every atom in your body, except for some of the hydrogen, was forged inside a star that lived and died before our sun was even born. The calcium in your bones came from an asymptotic giant branch star. The iron in your blood came from a supernova explosion. The oxygen you breathe, the carbon in your DNA, the nitrogen in your protein, all made in stars. We are truly children of the stars made of ancient stardust. Thanks for hanging out with me today at Nog's house. Next time we're going to talk about something even closer to home, the birth of our own Milky Way galaxy and our sun. I hope you'll join me for that. See you next time.